Okay, well, I'm not sure where the other, I know Julia is still sick, apparently, but I'm not sure where the boys are. But let's get started. So remember what we're doing. We're talking about what are we doing? Somebody tell me what we're doing. What kind of story are we telling? Anybody? Fields, okay. We talked about fields. We went from fields to ordered fields. We went from ordered fields to the real numbers, right? So the real numbers, we had the least upper bound property before fields, right? And least upper bound property plus ordered fields basically gives us the vocabulary to say that we have that we can define, basically describe the real numbers, right? The real numbers are an ordered field with the least upper bound property that contains Q as a subfield, right? Okay, and that's and then from there we said we're going to prove some basic properties of the real numbers. The first was the Archimedean property, which was the spoon and the bathtub, right? And then the second was the density of the rationals, right? That the rational numbers are, whenever you have two real numbers, you can always squeeze a rational number between them. Okay, so we're going to finish up with one last property of the reals, which is kind of answering the thing that answering the lack of the rationals that we pointed out at the very beginning, right? The big lack of the rationals that the Greeks themselves noticed was the lack of a square root, lack of square roots. Okay, and what we'll see is that so we've got reals, right? Reals are an ordered field with the least upper bound property and containing the rationals and the subfield, right? And what we're going to see is that as long as we've got this thing as long as we have this ordered field with the least upper bound property containing Q as a subfield, then you're guaranteed nth roots. You're guaranteed.
Sorry.
That's all right. You're guaranteed that you'll have roots. So here's the theorem that we're going to start off with and finish the reals with. For all real positive numbers and for all natural numbers, there exists a unique. So this, if I write like this, it means there exists unique. I don't know if you've seen this notation before, but there exists backwards E, okay? Okay, backwards E with exclamation point means there exists a unique. Sometimes people say like with a one next to it, there exists a unique, but I think it's more common for people to use exclamation point. Okay. There exists a unique y, so real number y, it's also positive, such that y to the n equals x. Okay. So given any positive number and any n, you're guaranteed nth roots. You're guaranteed a unique positive nth root. Okay. Okay, everybody all right? Okay, so the proof, we'll start off with noting that uniqueness is obvious. You can't have two numbers whose nth power is x, because if you had two of them, right? If there were two, well, one of them, suppose there's y1 and y2, right? One of them is going to be bigger than the other, and then when you take the nth power, that's still gonna that inequality is still going to hold, right? So if this one's nth power is x, well, this one's nth power is not going to be x, and vice versa, right? So you can't have two numbers with this property. Okay. Those of you who are coming late, we're showing that the real numbers have the property that given any that nth roots exist. Okay, nth roots exist. Right? Given any positive number x and any natural number n, you're guaranteed a unique positive number whose nth power is x. Okay. Okay. And first thing we notice is that uniqueness is obvious. Okay. Right. Okay. So we want to show that there is such a number, and basically our only tool is the least upper bound property. Okay, that's our main tool, as you may have noticed. So we have only one trick. Only one trick. The least upper bound property. Okay. Okay. So what we're going to do is kind of an obvious thing to do. I think it's very natural. You say, well, let's create a set of real numbers, positive real numbers, whose nth power is less than x, right? And then what we're going to do is take the least upper bound of that set, right? We'll use the, right? And that, so we're taking all the numbers whose nth power is less than x. The least upper bound of that ought to be our nth root, right? That's the strategy, right? Create this set of things whose nth power is less than x, and then the least upper bound should be equal to x. Okay. Okay. So okay. So we need to, in order to use the least upper bound property, we need to show a couple things. First is that E is not empty, and second is that E is bounded above. Right. In order to use the least upper bound property. Okay. So let's go for the first one. So first thing we do is we say, well, consider t equals x over 1 plus x. Okay. Okay. Look at this thing, and you notice that 1, it's smaller than 1, right? So first observe. This guy is smaller than 1, t is smaller than 1, right? Because the denominator is bigger than the numerator. And the second thing you notice is that it's smaller than x, right? Because you're dividing by something bigger than 1 on the bottom, right? You get x divided by something bigger than 1. Okay. Okay. So t is bigger than 1. T is smaller than 1. So that tells you that t to the n is smaller than t, right? Because you're multiplying by, every time you multiply by t, it gets smaller, right? Thing is smaller than 1. Okay. T is smaller than x, right? So that tells you that that t is smaller than x. So that together, that gives you that t to the n is smaller than x, right? So t to the n is smaller than x, which is what we wanted, right? We've created a t that lies in E. Okay. Okay. So should I go close your eyes for a second? Should I go faster, or anyone wants me to go faster? Raise the finger. Wants me to go slower? Raise the finger. Okay. It looks like we're about at the right pace. Okay. 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 So E is not empty. And then the second thing we want to note is that E is bounded above. Okay. So consider no. Suppose you have a number t that's bigger than 1 plus x. Okay. Okay. Well then, t to the n is going to be bigger than t, right? Right? T to the n is bigger than t because t is bigger than 1, right? So, and t is bigger than x, right? T is bigger than x, right? So, if t is bigger than 1 plus x, then t to the n is bigger than x, right? So, so what does that tell you? That if t is in E, right? If t is in E, then t to the n is smaller than x, right? So that means that t must be less than or equal to 1 plus x. Is that logically clear? Right? If t were bigger than 1 plus x, then t to the n would be bigger than x. But if t is an e, then t to the n is less than x, right? So t cannot be bigger than 1 plus x. T must be smaller than or equal to 1 plus x, right? Right. I mean, we're just taking the contraposition of this statement, right? If t is bigger than this, then t to the n is bigger than this. Contraposition would be t to the n being less than or equal to x forces t to be less than or equal to 1 plus x, right? So this is the contrapositive statement, right? And so if you're in E, you definitely have t to the n less than or equal to x, which means that t would be smaller than 1 plus x. Okay. So what does that give you? That gives us that anything in E is smaller than 1 plus x, and so we have an upper bound. Okay. Is that right? Okay. Okay. Okay, great. So what does that give us? We can use the least upper bound property. E is not empty and has an upper bound, so E has a least upper bound. E has a least upper bound. Let's call it Y. Okay, so I'm gonna erase here. Okay. Okay, so now, like we said, we're going to show that y must be the root that we're looking for, right? Our claim is that y to the n actually equals x. Okay, and we're going to prove this by contradiction. Okay, what we're going to do is see that if y to the n is less than x, then we get some sort of contradiction, right? And we'll also, I'll leave it as an exercise to show that if y is greater than x, we end up with some contradiction. It's the same sort of argument. Okay, so we'll just show the first part. If y to the n is less than x, then we end up with some contradiction. So we'll see that the strategy is to show that if y to the n is less than x, if y to the n is less than x, then we can find a small number h, such that y plus h to the n is also less than x. Okay. But remember, y was supposed to be the least upper bound of things whose nth power was less than x, right? But this would be something bigger than that, bigger than y, that still satisfies that, right? And so that would contradict y being a least upper bound, right? It would contradict y being an upper bound then. Okay, so that's our strategy. We're going to find some tiny h that we can, basically what we're saying is that here's x. If y to the n is less than x, then we can find some tiny h so that y plus h to the n is still smaller than x. Okay, so that's what we're going to do. Okay. So okay, so the yeah, so yeah, and let me we're going to find a small h such that this happens. Equivalently, a small h such that y plus h to the n minus y to the n is smaller than x minus y to the n. Okay. Which is, of course, the same statement. Right? I've just subtracted y to the n from both sides. Okay. So that's what we're looking for. We're looking for a tiny h that makes this happen. Okay? Okay. So this thing here, the structure of this thing here motivates the following lemma. So we're going to use a lemma observing that, so if you have two positive numbers, then the difference of their nth powers is smaller than b minus a times n to the b, n times b to the n minus 1. Okay. So, okay. So, a lemma. Everybody seen lemmas before? You know what a lemma is? Lemma is just a tool, basically. So it's like it's something that you use to prove a theorem, but it's not, maybe it only exists, it's only useful in this one case and maybe nowhere else. So you don't, like theorems are things that become like, have sort of, like more general application, right? But a lemma is a very specialized tool. But there are sometimes lemmas end up being really important. So there are like things like Schur's lemma, Zorn's lemma, these things that actually probably should have been called theorems. But anyway, they started off as lemmas and they remain lemmas forever. Okay, so here's this lemma, right? Because we're trying to find an h so that this thing is smaller than this thing, right? So what's going to be useful for us is to get something, to get something about differences of nth powers, right? We're gonna try to get a control on this difference of nth powers and make it smaller than this. So this lemma will basically give us some sort of intermediate. We're gonna see that this thing is smaller than something else, and then make that thing smaller than this. Okay, and that's how the lemma is going to help us. Okay, so anyway, b to the n minus a to the n is smaller than this, and the proof is just the following. So observe that. I don't know if this was something that you've ever seen before, but a difference of nth powers. If you just take the difference of the first powers, then it divides cleanly into the difference of nth powers. I know this is just a sort of algebraic fact that you may have seen before. Like if you have a squared minus b squared, well, a minus b divides cleanly into a squared minus b squared, right? This thing has one of its factors, a minus b, and it has another factor, right? Right. Similarly, a difference of cubes, a minus b factors cleanly into that. A difference of fourth powers, a minus b factors cleanly into it. Okay, so if you work out the division, what happens is that b to the n minus a to the n is b minus a times b to the n minus 1 plus b to the n minus 2, a plus b to the n minus 3, a squared, plus all the way down to a to the n minus 1. Okay, so this is just an algebraic observation. If you want, you can just multiply these two things together. You'll see that a lot of cancellation occurs, and then you get b to the n minus a to the n, right? It'll take you like 10 seconds, 30 seconds to do it. Okay, so there's this algebraic observation, right? You're trying to get control of this thing, and you remember, oh look, there's this sort of thing, and then you say, okay, well, b is bigger than a, so I'm going to replace all of the a's by b's. Okay, I'm going to replace in this term here. I'm going to replace all of the a's by b's, and this term is just going to get bigger, right? Because b is bigger than a. So I know that this thing here is going to be strictly less than b minus a times b to the n minus 1 plus b to the n minus 2 times b plus b to the n minus 3 times b squared plus b to the n minus 1. Right. All the, whoops. Yes, that's right. So all of those terms you notice become b to the n minus 1. Right? And there are n such terms, right, if you count them. So there are n terms, each of which is b to the n minus 1. And so you get b minus a, b to the n minus 1, and b to the n minus 1. Yes?
Wait, sorry, can you explain again why we're allowed to just replace all of the a's with a b?
Well, we're just making something bigger, right? Like if I had, 3 is less than a. Well, b is bigger than a, so I'm gonna, this is definitely less than, I definitely have 3 is less than b.
Oh, okay,
Right?
because it's just an inequality, right?
Yeah, all I'm doing is just taking this term here and then giving something bigger, and it's okay because I'm not trying for an inequality. I'm not trying for an equality, but an inequality. Okay, good. Yeah, so I'm smiling because I'm reminded of a sort of opaque joke that a mathematician once made, that an analyst once made. He said that somebody had asked him, he's an analyst, right? And somebody had asked him, what's the difference between algebra and analysis? And he said, in analysis, they use equal signs. And in algebra, they use equal signs. And in analysis, we use unequal signs. Anyway, it didn't strike me as funny then. Somehow it strikes me as really hilarious now. But anyway. Okay. Okay, I hope that was pretty clear, right? So you've got this thing. Okay, so you've got this inequality, which is useful. Everybody okay? Okay, I'm going to erase this because regrettably I don't have much board space, and I think that's easy enough that you don't have to. Hopefully you got it. Okay, so now we've got this lemma, right? The lemma says that this difference is smaller than what? Well, so by the lemma, so that was the end of the lemma. So back to the proof by the lemma. We know that y plus h to the n minus y to the n is smaller than b minus a, which is h, right? Right? This is our b, this is our a, right? H times n times b to the n minus 1. Right? Right? So that's what the lemma tells us. This is smaller than that, right? And what we want, remember, we want h so that this thing, right, so that the left-hand side is smaller than x minus y to the n, right? So if we can find an h that's small enough that this thing is smaller than this, we're done, right? So we've got this sort of intermediary bound. If we can show this intermediary bound is smaller than this, then we're done. What? Can I ask you not to use your phone?
Yeah.
Thanks. Thanks. Yeah. Okay. Okay. So we want to find an h such that this thing is smaller. This thing is smaller than this, right? But actually, we're going to do something a little bit. That's actually a little bit tricky. That's actually a little bit tricky. But what we can do. It's a little bit tricky because of you've got h here and you've got y plus h to the n minus 1 here, right? So what we're going to do is notice the following. So notice that that without loss of generality, we can assume h is smaller than 1. Okay. Remember, we're trying to find a small h less than big that's positive, and so initially we're saying that h can be. We're trying to find any h that's bigger than 0. So we're adding on an additional condition here that h must be smaller than 1. Okay, that's just making things harder for ourselves, basically. We're saying we don't have the freedom to look over the whole real line. We're going to restrict ourselves to the interval 0, 1. Okay, so this is okay because it's just adding on conditions. So it doesn't, we're not making things easy for ourselves. We're making things harder. Okay, so it's okay to assume that h is smaller than 1. Okay. So without loss of generality, we can assume h is less than 1 in that case, but then h and y plus h to the y minus 1 is less than h and y plus 1 to the n minus 1. Right? Okay. And if we can find h small enough such that this thing, right, h and y plus 1 to the n minus 1, is less than x minus y to the n, we're done. Okay. Okay. Everybody all right with that? Okay. Okay. So, yes, everybody okay? Okay. So, okay. So, but this is easy. This is easy. Just take, take h between h bigger than 0, such that h is smaller than x minus y to the n over n y plus n to the n minus 1. Right. Sorry. Let me call this guy h prime. Okay. H prime. Then letting h be the minimum of h prime and say a half will do. Okay. Why am I taking h to be the minimum of h prime and a half? I'm doing I want h to be smaller than 1, so I'm saying let's take n. If this thing is bigger than a half, let's take a half. Okay, right. So we know that, so 1, h is going to be smaller than this thing, and h is smaller than 1. And h is smaller than 1, right? And so what does that give us? That gives us that right? That gives you that y plus h to the n minus y sub n is smaller than smaller than h and y plus n to the n minus 1, which is smaller than x minus y to the n, and you're done. Okay. Right. So this part, right? This part is due to the lemma, right? And then this part here is due to our choice of h. Right. By the lemma, this is true. Well, really, this is true, and then our assumption that h is smaller than 1 gives that this is true, right? And then our h was chosen, right? Our h was chosen so that it's smaller than, so that h is smaller than this. In other words, h times this is smaller than x minus 1, x minus y to the n, right? So since our h satisfies this, right, this inequality holds. Okay, and so we get the inequality that we wanted, right? Right, we get the inequality that we wanted. In other words, y plus h to the n is smaller than x, right? And that gives us our contradiction. Okay, so everybody try to get it? Should I run it? I'll run it again. Okay, I'm just going to sort of sketch it out more concise. I'll just sketch it out. We wanted to show that if the supremum of the set we created was actually not the root, but smaller than but had an nth power that was smaller than x, then we could find something bigger than it whose nth power was still smaller than x. Okay, that was equivalent to this statement, right? That was equivalent to this statement. Then we used the lemma to get an intermediate bound. We said, well, look, this thing here is smaller than this, right? So if we can get this smaller than this, we're good, right? But this thing here is smaller than this, right? So if we can get this smaller than that, we're good, right? But then we said, well, in order to make this smaller than this, all we need is to choose an h that's smaller than x minus y to the n over n y plus 1 to the n minus 1, right? Because those are equivalent statements, right? In order to make this thing true, h has to be smaller than this, right? And we can do that, if you want to be finicky about it, we can do that because of the density of the rationals, right? We know we've got this real number and this real number, and density tells us we can find a rational number between those. Okay, so so it's possible to find an h that makes this true, right? And so we're done. And so we're done. Yeah.
I think I understand the purpose of why. Like from the lemma to that y plus 1, you want to get rid of one of the h.
Why do we want to get one of the h's? That's a good question.
Yeah.
Why can't we just go from here and then say choose an h? So why can't we just say choose an h so that h n y plus h to the n minus 1 is less than x minus y to the n, right? Why can't we do that? It's not so simple, right? Because how do you choose that h?
Yeah, and that's why you should be.
That's why we place this h by 1. Because then we can just divide both sides by this thing and say this just means h must be smaller than that. Okay, but if we divided both sides by this thing, we'd have an h.
Why 1? Why 1 in this
It doesn't
case?
matter. You could say 2.
Okay.
That doesn't matter.
And then so if we restrict h to be smaller than a natural number, a fixed constant natural number, and then you got these inequalities and you got the h equivalent, and now because x and y varies here, you want to take the minimum of that.
Why is the supremum of that? Why is the supremum of the set? It's a constant.
Yeah, but so my next question is that what if you don't choose the 1/2? What if you just keep it with the h is less than the constant number you chose?
How do you know that h is smaller than 1?
No, why do you have to choose 1/2?
Because I chose 1/2 to ensure that h was smaller than 1.
So the minimum, like if you don't choose 1/2, then it can be still there and it can be still greater than 1. Okay.
Yeah, I'm a little,
Okay.
I'm a little worried. Yeah, I
This
it's-
kind of new thing to me, like kind of new niche.
Okay, okay, okay,
That makes sense.
okay, okay, okay.
But you can choose whatever constant less than 1, right?
Yeah,
Okay.
yeah, yeah. Yeah, I think we have to do that, but let me double check.
Mhm.
I think we do need to do that. Okay, it just occurred to me while I was writing that we need to do this, we need to play this last trick. Okay, but I hope you guys see why we needed we couldn't just divide both sides by this thing. Right, because if we did, we'd be saying, take h so that h is smaller than this thing, oops, that's a y plus h, the n minus 1. Right, in that case, we've got h on both sides, and the question would be, how do you know you can do that? Right, how do you know you can do that? If this is a 1, we know we can do that just because of density, right? You can choose a number smaller than that. Okay, so that was the hardest thing we will do today. Okay, so yeah, so that's all we want to say about the real numbers. The last part of the section is talking about the complex numbers. So complex numbers, and it's also talking about so-called Euclidean spaces. Euclidean spaces. So these are things like, r to the n or c to the n. Actually, I think we just stick with r to the n. Okay, so complex numbers are another example of a field. Euclidean spaces are not fields, but they are examples of these things called metric spaces. And really, this is a course about analysis on metric spaces. Okay, so I know that some people mistakenly call this course real analysis, but it's really metric space analysis. It's not real analysis. Okay. It's really just analysis. Okay, so complex numbers. So just now we talked about R. What we're going to talk about now is if you take the plane R2 and we want to change that into a field. Okay, we want to make that into a field. It's an interesting fact that that's the last number for which you can do this. R3 cannot be made into a field. R4 cannot be made into a field, et cetera, et cetera. So here's how you do it. You say, so consider R2, which is just pairs of real numbers, A being reals, okay? And you define an addition on it by sort of the obvious way, adding component-wise. AB plus CD equals A plus C, B plus D. Right? So you just add things component-wise. You define a multiplication on it in the following way. AB times CD is going to be AC minus BD, comma, AD plus BC. Okay. So if you take this set with this plus and this addition, it actually turns into a field. Okay, so F plus dot is a field. Okay, in other words, it satisfies all the field axioms. Okay, right? There's an additive identity, there's a multiplicative identity, there's everything that you want to happen. There are multiplicative inverses, right? In other words, you can divide and everything else that you like. Okay, so and it's usually given the name the complex numbers. Okay, so these are this is actually the complex numbers. Okay, so I'm not gonna I'm not going to prove all the field axioms for this. It's not that interesting. But let me just do a couple of them. Right? You notice that if you take 1, 0 times C, D, right? What you get is you know, A is 1 and D is 0. So you get C, and A is 1 and A is 1 and B is 0, and so here you get D. Right? And so you see that this is the multiplicative identity. Right? This is the multiplicative identity. 1. You need complex numbers. Right? Right? Another interesting one is that if you take if AB is not equal to 0, 0, so kind of obviously 0, 0 is the additive identity, right? You know, adding 0, 0 onto anything will just preserve that, right? So if AB is not the origin, then A over A squared B squared, negative B over A squared B squared is the multiplicative inverse of AB. Okay, so if you multiply these two guys together, then you get the 1, 0. Okay, so in other words, this times this, if you work it out, becomes 1, 0. So this guy here is the multiplicative inverse. Okay, so you notice sort of pictorially, if this is A comma B, then A comma negative B is here, A comma negative B is here. And then here, you're dividing by the length of the vector. You're dividing by the length of the vector. So what you get is, you know, the vector, if this is a unit circle here, you're getting this thing here, right? And the product of those guys will give you the 1, 0. Okay. Okay. What's 0, 1 times 0, 1? What's 0, 1 times 0, 1? Well, you're going to get, right? You're going to get AC, which is 0, minus BD, which is 1, right? Actually, before I do that, sorry. So I ruined the joke. Okay, so here's a remark, an important one. R is a subfield of C. R is a subfield of C in the sense that if you take the real line, okay, you take the real line, here is the complex plane. Oops. Here's the complex plane here. Okay. If you take the real line and identify everything here with the x-axis, okay. So you map, you create a map. Let's call it phi. So map the number to x comma 0. Okay. Then it turns out that everything, the multiplication of x matches with the multiplication of c. Okay, right. That right. You notice that if I take x and y here, and I add them together, of course I get x plus y, right? If this is 0, say I get x plus y. if I go down to the complex plane and I take x comma 0 and y plus y comma 0, I get x plus y comma 0, right? So the addition is preserved, right? The addition of R, if I use this map, the addition is preserved. What happens, if you can add them up here and then map them, or you can map them first and then add them, and you get the same thing, okay? Similarly for multiplication, right? If I multiply here, I'm gonna get x times y. If I multiply down here, it'll be xy comma 0, okay? So this map is a one-to-one onto map from R into the onto this x-axis that preserves the field operations. Okay, so in that sense, R lives inside of C. It's what's called a field isomorphism. Okay, don't have to know that, but anyway. So it's an ordered subfield of C. Okay, so you can think of this thing here as R sitting inside of C. Okay. Okay. Should have erased that. AC minus BD, AD plus BC.
I have a question.
Just a second. Let me say one more thing, and then you can ask your question. So now here's a question. What's 0, 1 times 0, 1? Right. So you work it out, right? A times C minus B times D, that's -1. AD, 0, plus BC, 0. 1, -1 comma 0. Right? Okay. So what that says is that if you take this point on the complex plane, 0, 1, and you multiply it by itself, you end up with -1 comma 0, which in the real world is, in the real line is -1, right? So in other words, this is the square root of -1, right? And this is what you call I, right? The square root of -1. Okay. Oh.
Yeah, I just wonder that multiplication sign. How is the first term being defined as AC minus BD? That how is this somehow related to linear algebra for like a second, or is this a thing that people ask?
It is related to linear algebra. Let me get back to you on it because we're kind of out of time.
Okay.
But let me show you one thing that might. I don't know if this will make things clearer or less clear, but there's actually a geometric interpretation of complex multiplication, which is that if you have one complex number and another complex number, you have two complex numbers. When you multiply them, there's a geometric meaning to it, which is that you take the unit circle and then take this triangle here. Okay, take this triangle here, and then you scale it so that this becomes this length here. Okay, so you take a similar triangle. You take a similar triangle, and then this here is C times W. Okay, what's happening is that you're actually adding the angles. So when you multiply by something, it adds the angle on. So like this W has this angle here. Here's Z. You're going to add on the angle of W to that of Z. And then you take Z and you scale it by the length of W. You scale Z by the length of W. So you multiply this thing by that length, right? And you get this thing. Okay, so there's this geometric interpretation. But yeah, there is definitely a relation with linear algebra. I don't know it off the top of my head, but I'll look it up and I'll get back to you. Okay. Okay, that's it for today. See you guys next time.